Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's up everyone? Over the next few weeks, we'll be exploring just a bit of the great research that was showcased during last week's CVPR conference. Before we get to today's episode though, I'd like to send a huge thank you to our friends at Qualcomm for their support of the podcast and their sponsorship of this series. Qualcomm AI research is dedicated to advancing AI to make its core capabilities, perception, reasoning, and action ubiquitous across devices. Their work makes it possible for billions of users around the world to have AI-enhanced experiences on Qualcomm Technologies-powered devices. To learn more about what Qualcomm is up to on the research front, visit twimlai.com/Qualcomm, Qualcomm. Next up, a quick community update. If you're interested in the topic of causal modeling in machine learning, but missed out on the initial cohort of the course we hosted with Robert Osazuwa-Ness, I'm happy to announce the second cohort of this course and study group will be starting soon. For more information, join us this Thursday, June 25th, for a live webinar that Robert and I will be hosting to introduce causality and review all of the details of the course, including the many enhancements he's made this time around. For more information, visit twimlai.com/causal. And now, on to the show. All right, everyone, I am on the line with Babak Ehteshami Bejnordi. Babak is a research scientist at Qualcomm AI Research. Babak, welcome to the TWIML AI podcast.
Thank you for having me.
It's great to have an opportunity to chat with you, and I'm looking forward to learning a bit more about your research and what you're up to there at Qualcomm. But to get us started, why don't you share a little bit about your background and how you came to work in AI?
Sure. So I did my master's in electrical engineering at Chalmers University of Technology in Sweden. And in that program, we had a bunch of courses like machine learning and pattern recognition, as well as some image analysis courses, which kind of drew me to this field. And I decided to do my master thesis on cervical cancer diagnosis using ML. So kind of in the medical imaging domain. And I absolutely enjoyed it and decided to do a PhD in the similar field. So I came to the Netherlands in Radboud University. And I, for my PhD, I was developing machine learning models for breast cancer diagnosis in histopathological images. Histopathological images are microscopic images of tissue. And kind of in the early mid part of my PhD, this deep learning revolution happened. And me and a lot of my colleagues quickly switched to use deep learnings and get familiar with training it ourselves. And kind of moved to using that in my entire project. And during my PhD, I also organized the Chameleon Challenge. It was a challenge on finding cancer metastases on breast tumor patients. And it turned out to be a very successful challenge and was one of the first examples in which using AI, the top leading algorithms were actually outperforming human experts. We compared the top two algorithms in the challenge with a panel of 11 pathologists, and all they were actually beating all the 11 pathologists without exception. I also did visiting research at Harvard, at Beck Lab, and also towards the end of my PhD, I decided to join Qualcomm, where I'm here for a bit more than 2 years now, and I'm mainly working on conditional computation.
What is conditional computation? Tell us a little bit more about that.
So conditional computation in the context of neural networks refers to a class of algorithms that can selectively activate its units conditioned on the input it receives, such that on average, we have lower computation costs. And when I'm speaking of units, it could be layers or individual filters, for example. And the thing is, in our feed-forward neural networks, we usually have this prior that no matter what input it is receiving, we always run all the layers, all the filters, no matter what. While in reality, some examples might be simple and some harder. And maybe for simple examples, we could exit earlier from the network and finish the classification. Or sometimes we're, for a classification task, classifying the image of a cat, and sometimes classifying the image of a vehicle, for example. But now, even in the middle of a network that we are kind of certain that we are dealing with a picture of a cat, we are still applying all those vehicle detection features or filters in our to our feature map, which is superfluous, and also from a generalization perspective, that is bad for our network. So conditional computation aims to selectively activate parts of a network. It could be different layers, it could be channels, it could be actually a whole subnetwork in your main network, which you could completely deactivate. In fact, if we want to look back, the first examples were maybe by Geoffrey Hinton and Robert Jacobs from 1991. They had a paper, Adaptive Mixture of Local Experts. And the idea there was they trained a giant network with many small sub-networks, which were experts for a specific subset of the data. And then there was a gating network, which would get the input as well. And based on the input, it decides which of these sub-networks should be selected. And in that way, they were kind of encouraging the network to be expert, these sub-networks to be expert on their own specific data. And also in recent years, in the era of deep learning, we see more of the more approaches are using conditional computation. Maybe one of the early examples was BranchNet, which adds auxiliary classifiers in your network. Let's say some early in the network, some in the middle of your network. And the aim is that easy examples should exit earlier. Another work which was an inspiring work, was convolutional networks with adaptive inference graphs, which basically decides to gate, basically activate or deactivate individual layers in a ResNet block, condition and input. They hypothesize that maybe some layers are important for specific classes, but not for the others, and they could learn how to turn on and off individual basically layers in a network. And they were actually inspired by their own previous works, which showed that if you actually delete individual layers in a ResNet model at test time, its accuracy will not drop. That was very interesting. Of course, on the layers which you have stride 2, so a downsampling, you might get a little bit of performance drop, but on the rest of the layers you didn't get. So they decided to learn when to drop. And this is also in sharp contrast to other types of confidence, like VGG network. You cannot actually do that, because if you drop a layer, the whole sequential part will break. But in ResNet, it was perfectly doable. And that actually constituted the basic idea for what we want to do as well, which was starting to gate channels instead of layers.
Before we get into the details of your specific research, are the conditional computation techniques that you're applying exclusively focused on inference, or conceptually, it seems like you could apply it to both? Is that right?
Yes, exactly. You could definitely apply it to at training time as well. So there's like an if else argument inside your training, for example. If it is saying deactivate, you could choose not to send the gradients toward that part of a network. And you could basically gain speed or inference training time, and also inference time as well. Sure.
And the specific techniques that you focus on, are those more concerned with inference time?
Yes, our main focus has been on inference time. We try to it is definitely possible to do that for training time as well, but we mainly focus on inference time speed up. Yes.
With the overarching implication that you're trying to reduce the power and cost of doing inference on a device.
Right, exactly. So maybe that is actually not the only motivation.
Okay.
Interestingly, if you train such networks, these networks tend to perform much better than counterpart like a fixed neural network with the same computation cost. And I will describe that in a bit. That the reason is that these models tend to, you can start training a very giant model, but then at inference time, select only very limited subset of the resources available, condition on the input. You say, okay, this network is huge, but you should just pick the relevant ones. It induces the network to become to have expert subnetworks inside the network as well, because by gating, it understands, okay, these subset of filters should be activated for cat detection, and the rest maybe for vehicle detection. So it actually, interestingly, improves the performance as well, which is a good thing.
Well, why don't I take a step back and have you kind of describe, at a high level, the different types of approaches you're taking in these papers, and then we can dig into more specifics.
Sure. So in the first paper, which was batch shaping for learning conditional channel gated networks, we were basically thinking, instead of gating individual layers in the network, let's make it more fine-grained and gate individual filters. That would give us basically more flexibility and more power, representation power. It would allow us actually to gain more interpretability as well, to understand which filters are firing for what classes. So that was the main focus of the first paper. The second paper, which was on continual learning, actually before starting the second paper, we already knew that this idea of channel gating would be very useful for multitask learning and continual learning. Because, for example, in multitask learning, one problem they have, so we know that if you want to learn a couple of tasks together, generally tasks might help each other, so that the performance gets a little bit improved in general, because they share the features among them. But as the number of these tasks increase, suddenly you see the performance actually starts dropping. And that is because of feature interference. By forcing a specific task to use a feature which is not relevant for the task, it actually starts degrading performance. And we thought that if we could use our gated networks, we could decide when to activate or deactivate features, and not allow feature sharing if a feature is not relevant. And in continual learning, these gates could actually serve as memory, which would allow us that if a feature is particularly important for a specific task, maybe we have to preserve it and not allow other tasks to update it too much. And in the last paper, we mainly focused on long-range activity detection videos for classification. And we thought we might get as input a video which is like 10 minutes, but we know that there is a huge amount of redundancy and irrelevant things happening which are not really important for the actual classification task. And we did dynamic gating of individual snippets in the video to only focus on the important parts, and actually saved a huge amount of computation based on that.
Okay. Well, let's jump into the first paper, because I have some questions there. You mentioned that this paper is kind of shifting from thinking about gating layers to gating individual filters. What are the specific types of filters you're gating here?
Sure. So the design is something like this. Assume that we have a ResNet block. We are augmenting this. Well, we are adding to this ResNet block a gating module. This gating module gets the same representation that goes to the ResNet as input. And its output is a bunch of gates. And the number of these gates is equal to the number of filters, let's say, in a first convolutional layer of the ResNet block. So one gate coupled to each filter. And the filter wants to activate or deactivate the use of that filter. And we had a bunch of criteria. For example, we wanted the gating module to be very light because we didn't want to have a lot of additional overhead. We wanted the gates to be input dependent, so that they don't make just arbitrary decisions, but they see the input and condition on the input, make a decision. And last, we wanted it to make a binary decision. We didn't want it to be like an attention, because attention would not save you any compute. We want it to be 0 or 1, which means it would have been a discrete optimization problem, and we used Gumbel softmax for training this network. But it was very interesting problem, because we started training this model. And from the very beginning, if you have, let's say, it's a classification problem, let's say, and you have the cross entropy loss, the gates automatically want to learn the most trivial solution, which is just be on all the time. And by being on all the time, they satisfy the objective of the cross entropy loss. And it's as if you're training a boring regular network. It's just a standard regular network. While we wanted the gates to behave conditionally, to be sometimes off for certain types of input and sometimes on. And for that,
And now you're training this network kind of all at once. You're not separately training the gate layer and the
no,
network itself,
exactly.
right?
We are training end to end all at once. Exactly.
Okay. Yeah.
So then we started saying, okay, we want to sparsify these gates. We don't want it to be always on. And by doing that, we found out actually, if you, for example, apply L0 loss, a lot of gates turn out to be permanently off, which is actually not interesting either, because permanently off would be equivalent to these model compression techniques, like pruning techniques. We want the gate to be at the same time, sometimes on and sometimes off. And interestingly, when we decided to encourage entropy to have a higher entropy, let's say sometimes on, sometimes off, these gates could easily cheat. They could generate a probability distribution centered at 0.5. So assume at the output of the gate, you pass it through a sigmoid and then take the argmax or a threshold at 0.5. It could put the distribution centered at 0.5 that when you add the Gumbel noise, and take the sample, it is randomly on and off. It's not really learning,
Right.
it's just randomly. So it had learned to be a random dropout, which was really not something we wanted. What we wanted in contrast was a U-shaped bimodal distribution, which means for certain type of data, the output is 1, and for certain data, it is 0. And we said, okay, we have this strong prior. Why don't we actually help the gate to have a distribution like this? And with that came our other contribution, which was the batch shaping loss, which was inspired by the Kramer-Van Mises criterion. What it does, it basically takes our prior distribution, which is a beta, like a U distribution. We compute its CDF, and then we also compute the empirical CDF of our sampled distribution from the output of a gate for a batch of data. And then we minimize the distance between these CDFs. And interestingly, CDF is perfectly differentiable. The derivative of that of a CDF is PDF, so we could get that freely from the forward pass. And then the distributions perfectly matched each other, which was very interesting to see. And we think this batch shaping loss could be very interesting for a lot of other applications when you want to match two distributions.
Before we go into some of the applications, which distributions were matching one another?
It was a beta distribution. So we forced the gate to have a beta-like distribution.
Oh, got it.
Let's say 50% on, 50% off.
Okay.
Kind of. And that helped a lot the gate to behave more conditionally, because he knew that it can only be 50% on. So let's turn it off for whatever irrelevant type of data. And this helped the network to behave really conditionally. And we could also visualize when it is on, when it is off. And it was really making sense. And interestingly, we saw very good behavior of this network. We saw that we could actually take a ResNet 18 model. Let's make this ResNet 18 model incredibly wide. Let's make it 20x wider. But at inference time, we force it to make it so much small that it is the size of a standard ResNet 18 with width 1. So it has a lot of filters, but you're only allowed to choose among them such that the size doesn't change that much, but on average. So for more complex examples, it could choose more filters and easier, less filters. And this ResNet 18 at the inference time size could perform as good as a ResNet 50, for example. It performs much better than it's kind of an equivalent size network, which is with a fixed architecture. And
how would you compare the complexity of the very wide ResNet 18 with the ResNet 50?
So the complexity, we measure that in terms of MAC operations, so multiplication and accumulation operations. So it is much more cheaper than ResNet 50, of course. And we of course forced it to have with the sparsity to not use all the filters, so that inference time it is actually still the size of a ResNet 18.
When you were applying the batch shaping, is the idea that one of your parameters is how many of the gates are active? Is that how you were able to shrink down this wide ResNet 18 to a much more narrow one?
Yeah. So we had a prior for these for this beta distribution. The prior was actually being 60% on and 40% off.
Okay.
And we started with a very strong coefficient at the start of training. So all the gates are forced to take that shape. But as we go on, we slowly reduce that coefficient so that the model has a little bit more flexibility. And then we see that some of the gates might actually just get rid of that conditionality and go and be completely on. Those are maybe the filters which are very important, and it's like too fundamental. They need to be always executed. But there are some gates, the majority of the gates keep that shape, but we also added the L0 loss. And L0 loss has the ability to actually throw away if a filter is completely useless. So, for example, if due to poor initialization, some of the filters turned out not to be that useful for the classification task, it could actually push it down to completely off. So we have a combination of completely off filters and completely on filters, but the majority conditional filters. And the conditional ones take different shapes. Some of them might be 80% off, 20% on, and some of them 80% on, 20% off. And we, using the coefficient of these two losses, we control how much MAC we want to save, basically.
Now, it sounds like you if I'm understanding this right, you kind of set off with this idea of building these conditional channel gated networks. And when you saw kind of the gates, all on or all off or kind of flipping randomly back and forth, were these, presumably these were your initial experiments and they were surprising. Like, did you,
Definitely. Yeah.
I'm curious, as you were seeing these kind of results, how did you know to go to the batch shaping, as opposed to, I'm thinking about, maybe this just doesn't want to work, right?
Yeah,
Like
yeah,
you're trying all these things.
yeah, exactly. So, I had several meetings with Max Welling, and we had a lot of brainstorming sessions. And
Uh-huh.
very interesting. One day he came. So I was plotting the histogram of the gate output, and
Okay.
a lot of them were centered in the middle. And he was so sharp. Like as soon as he saw, he said, "Oh, these are like random dropouts. You want these U shape, right?" And I said, "Oh,
Mm.
yes, I want that U shape." But it said, "Let's think about how to make that U shape." And we thought of a lot of different experiments. For example, pushing the values to be away from 0.5. So the values tended to be in the center. We decided to make it pushing towards the two sides, but that didn't work. We tried the entropy as a loss. That didn't work because the gating module could easily cheat and
Mhm.
center everything in the middle. And a lot of losses actually led to not conditionality. So complete pruning, which is like static compression methods, which we were not interested. We wanted the conditional way of doing that. And over time, we thought that actually you cannot. So a single gate, you cannot cause a specific distribution without regarding the entire batch. So the whole point was that this distribution is only defined when you take the entire batch into account. So in this batch there is a collection of data points, and you want these data points to behave differently. So for some of them we want it to be on, and for some of them to be off. And we didn't know which ones are going to be on off. It's
Mhm.
just the network has to learn. And we actually didn't even know of so at least I didn't know of the Kramer-Van-Mises criterion. We came up with this loss. And then later stage, we found out, these Kramer-Van-Mises criteria did exist, and it was like proposed like 40, 50 years ago, but it was never used in the deep learning, and we made it like differentiable, and there's one key point inside that, and that when you get the output of a gate, you have to sort it, and then generate the CDF of the sorting values. And then during the backprop, you have to remember to unsort the operation so that the gradient goes through the right input and the right direction. So there were a bunch of tricks, but then we tried to basically narrow down the problem, make it as simple as possible to find out what makes it work, and this turned out to work.
Nice, nice. And you mentioned that this batch shaping technique you were starting to mention that this batch shaping technique has other applications.
Sure, sure. I'm thinking that it could potentially be used for whatever application in which you want. So you want to match the distribution of a parameterized feature in your network, let's say a feature map, to any distribution. For example, in batch norm, we may want it to be normally distributed. We could actually enforce that with the batch shaping loss. And basically, in whatever application that you want to impose a prior on the distribution of your feature maps, you could do that with this technique.
So the next paper where you're looking at task-aware continual learning, is that building on this batch norm or batch shaping technique, or is it a separate research in the direction of the conditional gated networks?
So it is a follow-up on the channel gated networks. We use the exact same type of network, but instead of applying it to ResNet, because we knew it would work for regular networks as well, like VGG type, we applied it both for regular types of models and ResNet models. So maybe I could briefly talk about the continual learning problem. Well, in continual learning, we have basically this setting that you want to learn a specific task, let's say task A, using a neural network. And you train this model using data from task A and get a very good accuracy, let's say. Then you go to task B, but you should consider that you will never have access to data from task A anymore. And now you want to train this previously trained model again, such that it performs very good on task B, but doesn't forget what it has learned on task A. In reality, the fundamental problem with continual learning is that we have the catastrophic forgetting problem, because as soon as you update the weights, they completely forget what they previously learned. And that is actually a fundamental problem we have in training neural networks. That's why when training, we train these models using many epochs, or we have to shuffle the data all the time. We cannot just take a batch and perfectly learn it and go to the next batch to perfectly learn it, because we keep forgetting. And this problem also arises in continual learning. So our idea was that we could use these channel-gated networks to bring several benefits. But let me before that tell about two very fundamental approaches which people use. One of them is basically maybe a work by DeepMind on elastic weight consolidation. What they do, they measure at the end of training on task one, they measure the importance of the individual filters using the diagonals of the Fisher matrix. That if a particular weight is very important, let's not update it too much. Let's slow down the learning on those weights, and the features that were less important, we could actually learn them better or make them more available for the future tasks. Well, obviously, the problem with this method is that as you go on and learn more tasks, you tend to have this trade-off between learning new things and not being able to change things previously learned. And this approach works very well on simple data sets like MNIST for let's say 2 or 3 tasks. But as soon as you increase the number of tasks, it fails. There is another vein of approaches which are basically progressive neural networks, which they say, okay, let's train our model on task A, and then when we go to the next task, let's add neurons and learn task B, and we have the ability to learn use previously learned features, but are not able to change them. The problem is with this approach is that as you add neurons, it will become really not very scalable, because your model is going to get huge. And also you're forcing to share previously learned features, which might be irrelevant for the current task that is coming. So, so our idea was like this. So we thought let's use our channel gated networks. So you have task one, you train it using our channel gated network, and each of the layers have a specific gating module which is specific for that specific task. So each task has its own gating modules. These gating modules are not only task dependent, but also input dependent. So they basically, during training, we basically enforce these gates to not use all the filters, because we want to make a lot of filters available for future tasks. So we impose a lot of sparsity. Let's say a specific layer has 100 filters. Using channel gated methods, we and sparsity, we enforce that it, for example, uses 20 of out of the 100 filters available. And because filters or these gates are input dependent as well, not all of these 20 filters will be actually used for all the examples. Some may use only 5 filters, some may be the entire filters. This makes these channel gated models extremely efficient and very with very low computational cost.
You're essentially adding the task as another input to the channel gate that you already had before.
Yes,
That was
that's
an
right.
input dependent.
Yes, but then we go to a new task. Now, the new task is going to have its own gating module. Well, these gating modules are actually very important things because if we study them, how they are firing, they could easily tell us how important the feature is. If a gate is firing too often, it means the filter is going to be used all the time. We should never change this filter. So what we do, we look at the most important features, and in practice, we actually even because of a heavier sparsification, if a filter is selected even only once, we chose to keep it and freeze it. So all the features or the filters that were important for task one, we freeze all of them. And all the rest of the filters which were not used, we reinitialize them and make them available for the new task. And the new task can obviously learn the new filters based on basically its own objective, but it also has the option using its own gating modules to choose to use previously learned features as well. It is not allowed to update them, but it can choose to use or not use them, which would make these networks to have positive transfer of information, but not forcing it. So if a feature is not irrelevant, it will not be shared. And you can keep growing and increasing more tasks. The great thing is that these gates are always input dependent. At inference time, they're extremely light. So if you make this network extremely wide, it would be super light at inference time because only a very small subset of filters are going to be selected at each layer.
And so, how exactly are you allowing the task to choose the filters from the previous tasks? Is this based on initialization or something else?
So just imagine we have a resonant block, and let's say in the first convolutional layer, we have 100 filters. 10 of them are frozen, so they are not. The gate is not, they are not updatable, and 90 of them are learnable. So the gating module gets the same representation that goes to these resonant block as input and chooses, okay, should I use this filter number one, which is not updatable or not? It makes a binary decision, pretty much like before, but it cannot update the filter. It just has to say choose to use or not. But for the rest of the 90, it can update them. And so we trained this model, and very interestingly, we saw that there are actually a lot of SOTA and very good methods already in the literature. And on 4 data sets, we were able to achieve as good or better performance than all competing methods. But then we wanted to make this a little bit more challenging. There is a specific setting in which you actually don't even know which task you are operating on. So up to now, we were assuming that you know which task you are going to work on at test time, and you would only activate that branch of the network and the gating modules of that specific task. But in some cases, you might not even know which task you are working on. And this is a very complicated setting, and there is not much work in the literature. And what we did was that so we assumed from the start of at the inference time. So you could train as usual, but at inference time, when you get an input, you would gate them with different hypotheses. This is task one. This is task two. This is task three. The same input. But at the end of the network, we added a task classifier, which looks at the gating patterns of this feature map, how this feature map has been altered based on different hypotheses, and based on that makes a decision that which task I should be classifying this network. But of course, this classifier at the end of the network is going to suffer from forgetting as well, because you have, as you increase the number of tasks, you have to retrain this classifier. And we chose to use a generative model to remember the data learned, the data that was used for previous tasks. So when we are training on task one, we are also using a generative model to learn to generate data from task one. And these generated samples are used for training the task classifier at the end. There are not that many methods, but there was one method from CVPR 19 that we compared against, and we were outperforming it on all the data sets by actually a very large margin. But it's still a very complex task. It's like
it sounds like your model is starting to get very complex once you start to add a generative model on top of everything you've already done.
Yeah, definitely. This is kind of a problem which is very complex already, and adding the complexity of the generative model and being able to generate very sharp and nice examples just adds more complexity to the continual learning problem.
And do you think that there's something in particular that you've done with the application of conditional networks that allows the generative model to work, or could you then, now that you've seen some good results with the generative model, take that back and apply that to other aspects of the network without the conditional gating for the unknown multitask problem?
That's a very good question. So first of all, these gating models, these generative models are not going to be used at inference time. We don't need them. It's just used for training basically the task classifier, and after training, you can throw them away. But we also actually thought about training this generative model using a unified giant generative model, which can be gated as well. In the same way that we are training this inference model. We didn't try that, but I think it would be an interesting idea to use gating for generating examples as well. So gating with task one, generate examples of task one, things like that.
We've got a third paper that we wanted to make sure to cover as well, and that's the TimeGate paper.
Yeah.
Refresh us on the setting that paper's looking into.
Sure. So in that paper, we primarily focused on recognizing long-range activities in long-range videos. So the problem with long-range activity, first of all, what do we call when do we call a video a long-range activity? So assume we have a 10-minute video, and all that is happening inside that video is a guy skiing, and the label of that video is skiing. That's going to be so easy to classify, because even if you look at a single frame, you would be able to classify the entire video. This we don't call a long-range activity. A long-range activity could be, for example, making a pancake, because it has so many atomic small action items which you have to recognize. Getting the egg from the fridge, for example, getting powder, scrambling or mixing everything together, and then putting on the pan. So it has a lot of atomic activities. And in order to recognize that this action is making a pancake, you have to identify all of these. But all of these could happen at different time intervals inside a 20-minute video. And if you want to go and classify frame by frame all these 20-minute video, it's going to explode. It's going to cost you.
Do you need to recognize all of that, or can you just recognize the round thing, kind of with bubbles and then getting flipped at the end, and then you figured out you're making a pancake?
It could be that there are a lot of classes which are similar. For example, scrambled eggs might be, making it scrambled eggs could be very similar as well. And maybe there are items like picking up the flour could also be a key item here that would help you identify that it's actually making a pancake. And picking out the flour by itself might not be enough, because the person could be making a very puffed cake as well. So you need really multiple things to be able to recognize the entire video.
So for this setting, you've got this long video with multiple tasks being illustrated, tasks in the human behavior sense,
Yes,
and you're trying to classify all of the entire video as one thing that's happening.
exactly.
Okay.
So one of the very common way of doing that is you divide this entire video into chunks of snippets, which, let's say, each snippet is 8 frames, and then you could give it to a very heavy model like i3D or a Resnet 3D model that would make a representation out of these 8 frames. And then you do that for like a sliding window all throughout your network. Then you have a classifier that looks at these features and does the classification. This is going to be extremely expensive. So what we saw that we could maybe actually do a gating using a gating module that dynamically looks at these frames and decides which parts of a video are interesting to look at. So our approach basically is made up of 2 steps. It has a very, very light classifier or basically network in the start, which gets a very compact representation of an input frame. Then we have a gating module, and this gating module is conditioned both on the segment and also looks at the context. So not only the current frame, but also at the other frames. And using this gating module, we are able to say whether this particular frame is relevant for classifying this video or not. And only the ones which are the most relevant, and we could also, similar to previous works, impose a sparsity so that the light network does not pick so many frames, only a limited numbers, and only the most relevant ones would go to a heavy network and do the actual heavy operation, which is common. We use the same models as well. And the good thing is that you could couple these light network with any model. You could actually use very super efficient models, which are also already implemented, and couple it with this gating module. It would still give you a lot of benefit. And no matter what model we use as the main feature representation extractor, we roughly saved half of the Mac operations. And even at that point, we slightly got improved performance. Maybe because we are able to help the network focus only on the relevant parts of a video and get over from the distractions and actually get slightly better performance even at half the computation cost. And this approach is definitely orthogonal to a lot of let's say compression techniques, because some approaches focus on making the models compact, and let's say you could basically do our channel gating on these models as well, or you could do static compression methods. And adding these gating modules to only focus on the relevant parts of a video could really bring down the computation cost overall.
And so is the use of channel gate or conditional gating in this context, how similar is it, in application as conditional gating in the other 2 papers? It seems like it's somewhat different.
It is somewhat different, actually. So we use the same Gumbel softmax trick for training these gating modules, but it is basically for training this, we thought of first extracting a bunch of concept kernels. Concept kernels could be extracted using let's say a network which is pre-trained on the data set you want to work on, and getting some representations. Let's say I want 100 kernels at the end, and you basically compress this data and say these are the core concepts of my data set, and then this gate as inputs instead of getting.
Is it before training or during training?
This is before the start of the training. This is an independent concept, so you could extract that anyway.
Okay.
And then for these gating, so previously we had, for example, as input to our gates, the representation coming from the Resnet block. Here it's very different. Here the gating module would get as input the representation coming from the last layer of the light network in the start of the model. So the light network first give us some representation, and using that, and also we do a dot product of that with the concept kernels to see if there is anything interesting in this frame, given the concept kernels that I know about this data set. And this dot product would go to our gating module. And this gating module will, of course, it uses the Gummel softmax trick, which we've been using previously as well.
I think I'm struggling with what is actually gated in this. Are you gating the kind of the input flowing into the kind of the overall network, or are you still doing something similar where you're gating, ResNet modules or filters or something like that?
The former.
Okay.
There is a light net and a heavy net, and if the light net says the current frame is irrelevant, the entire frame and actually this snippet around it. So we analyze the center of the snippet. Let's say we have 8 frames that goes to the heavy net,
Yeah.
but the light net only analyzes the middle frame of these among these 8 frames. And if it
Okay.
says no, it's not interesting, the
Just
heavy
drop
net
it.
would just completely not analyze the entire snippet.
Okay. And so you've got these 8 frames and you're analyzing the center frame. Are you striding, or is it 8 and then the next 8?
Uniformly sampled, and so
Okay.
uniform sample a lot of these segments. Let's say 8 frame, 8 frame, 8 frame until the end to cover the entire video. And the 2net only analyzes the center frame among these. Let's say the frame number 4, and based on that makes a decision: is the entire chunk of frames useful for the current classification task or not?
Are there other applications to this than video, or why
Yeah.
did you even go after this particular problem?
So we thought gating in general would benefit a lot in, let's say, classification problems, or we even tried that on segmentation problem as well. But a data set with the biggest amount of redundancy, we think, is video. Video, when you're analyzing video, there is so much correlation in different frames. You're basically observing the same thing over time that it makes it the most low-hanging fruit for gating operations. Uh, we are actually following up on a lot of tasks using conditional compute for video analysis as well, including video segmentation, classification, etc.
Apologies if you mentioned this already, but the specific results of this in terms of the videos and the computational complexity, all that, what did you end up finding?
So we found that, for example, no matter what heavy type architecture we use, whether it is the most complex ResNet 3D model, let's say ResNet 3D 101, or it's a very efficient model, we can reduce the cost by half while still getting slightly better performance than the original model. So we both save
Okay.
half and perform better. And one very interesting property of this approach is that it makes interpretability very easy, because you could immediately look at the chunks of video in the entire 10-minute video that are selected, and are they actually correlated? So you could very easily analyze if the gates are working properly or not.
And did you see any interpretability results in the other couple of papers or problems that you were looking at as a result of this?
Yeah, absolutely. So in the first work for the channel gating, we targeted some of the gates that would the most interesting gates are the ones which are very selective in firing. For example, only firing 5% of the times. If you look at them, the examples look very similar. For example, only tiny insects in the middle of grasses are detected by this particular gate. Or, for example, all the giant creatures in the water are detected by a particular gate. And then in the continual learning, we thought it would be harder to recognize these gates, to see differences, but it was very, very interesting. We looked at a gate which was running in all different tasks. Let's say the task was 1 versus 2 classification for task 1, 3 versus 4 for task 2, 4 versus 5, task 3, etc. And there was a gate that would activate whenever in the first glance I didn't recognize it, but then I focused and I said, okay, this gate is actually firing for all the bold phones, and all the ones which are like the tiny phones, which is the letter is not very bold, it would not fire. Which found that feature interesting, but it's in general it's a little bit more difficult when the number of classes is not huge to find interpretability. But for ImageNet, for example, it was very easy to see interesting to get interesting insights of what each
Yeah.
gate is doing. Yeah.
Yeah, this work in conditional gated networks,
Yeah.
yeah, how does this ultimately kind of get expressed in, products and things like that? What do you do with, this stuff that you're, learning and discovering?
So this is currently mostly at a research level, of course.
Hmm.
We have been so the entire vision is that we could probably at some point have a very very giant network that could be very sparsely activated. It could even work for multiple tasks, completely independent tasks, and then condition on the input, it would find out which path in the network it would actually should need to be activated. So at inference time, it's going to be very light. But of course, the first step that we talked to the software team and to see what are the requirements for making use of such models. And usually, our discussions were so we need to convince them that we need to implement the specific layers that would allow implementing this on our particular hardware. We are in the middle of a discussion and trying to use this channel gating in a number of works. But in general, a lot of times this when the trick that we are using or researching is straightforward, that could have very fast impact and go directly into the product. For example, one of my colleagues, Marcus Nagel and Martin Tijmen, have been working on a quantization paper which was from ICCV 2019, I think.
Hmm.
And this paper was working very well. They talked to the software team. It was immediately implemented, and it was suddenly like in a matter of a couple of months, it went to our Snapdragon platform, and people could actually use it. And then later on, we got in our private WhatsApp group, I got a message that this particular quantization method is now employed by this very famous app. I'm not gonna name it, but now suddenly maybe hundreds of millions of people are gonna make use of the technique that you developed. It was completely a research at some point, but now it is actually in your product.
Wow, wow. But something like this work, is it to what degree is it broadly applicable to a wide variety of applications? And in particular, we've talked about different applications that it can be applied to, but in each of those cases, you're kind of tuning the application of the conditional gating. I think quite a bit. Do you see a point at which this is a kind of off the shelf thing that's automatically applied across different use cases? What's the path towards making it generally applicable?
And that's a good question. I think so. I'm really advocating the use of conditional compute. In general, I think it is biologically also very relevant because a lot of the models of the brain say that the neurons are activated in a very sparse fashion. And it's not like a pruning method that some of the neurons are never activated. It's really dynamic. Sometimes some elements are activated and sometimes not. So I think this should definitely be a direction in the future. And I think it's kind of, it would be weird for me if the future of AI would be that we have, let's say for 100 applications, we have 100 independent models which are only trained with that data, and we run them all one at a time. This is not going to be the future. I think it would be a centralized model which would be very good in operating on multiple tasks at the same time, and it could sparsely get activated. So initially, when I talked to some hardware folks, they thought this might be a little bit not in maybe by next year, it may not happen, but they definitely see that this might happen at some point because they see the vision that this could be part of the future of AI models. And this immediately says that, for example, to get this implemented, you need an if-else statement. So if this happened, if gate says this operation, you need to do this, and else do that. So we need first to see what can be done by the software folks. And then if necessary, we could even reach out to the hardware folks to influence the next generation of even hardware, I think.
Well, Babak, thanks so much for taking the time to share with us what you're up to there. It sounds like really interesting stuff that I hope to see more of in the future.
It was my pleasure. Thank you very much for having me.
Thank you. All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.